Hey, I'm Bill Sky, the assembly guy, and in this video what we're going to do today is we're going to talk about dynamic memory allocation. Whoa, what's he talking about? Well, dynamic memory allocation, if you haven't watched my C++ pointers video, dynamic memory allocation is the ability for your program to allocate memory that it didn't think it needed. Like for instance, let's say you're going to ask the user to type in some data. Well, you can create an array of size 10, but what if the user wants to type in 20 items of data? You can't dynamically, without doing dynamic memory allocation, you can't make that array larger. You could do things like have them type in the first 10 and then save those 10 to a file and then have them type in the next 10 and what a mess. So dynamic memory allocation really makes it easy to, well, I shouldn't say easy, but it makes your program much more flexible. And also, you're not having to deal with wasted space. So one of the solutions is go ahead and create an array of 10 million, right? Well, now you've got 10 million, let's say, integers. That's 40 million bytes of data that your program won't need. Now, on a computer that has, 32 gigabytes of memory or 128 or 192 like mine, so what? But if you're dealing with smaller computers or not everybody has that big of a computer, you've got to worry about memory. So you can do the same thing in assembly language. In fact, you do it in assembly language. Even if you do it in C and C++, it's translated to assembly language during the compile process. So let's take a look at a demonstration of what I'm talking about here. All right, so I've got a C++ Eclipse program or project up here and running. Well, not running, editing. And what I'm going to do is I want to dynamically allocate some memory. So what I'm going to do is I'm going to dynamically allocate an integer. So I'm going to say integer asterisk, because when you dynamically allocate memory, you've got to put that address, the memory address that's allocated, in a pointer. You can't just assign it to any variable. It must be assigned to a pointer. So in this case, it's an integer pointer. That's what the asterisk means. And I'm just going to call it int ptr, a very unfriendly variable name, and I'm just going to say it's equal to null pointer. Now, why am I doing it there instead of down here? Because it's always better to put your variables up on the top so they're all defined up at the top of your main or the top of any function that you write. Now, some people might argue with me. That's fine. It's style. But remember that when you do this in a C or C++ program, all of the memory data, all the variables that you've got are put up in the data section anyway. They're always put up there anyway. So it's not like you're doing the compiler any favors here, but you are coding more like the compiler or the computer expects you to. So there's my integer pointer. Now, how do I actually allocate that? What I do is I say integer pointer equals new integer. And what that will do is that will allocate an integer in memory. It'll return the address of that and put it in int ptr. Now, in assembly language, you do the exact same thing. It's exactly the same way. Let's do another demonstration. Instead of using the new, you can do a thing called the malloc. And the way that you do that is you say int ptr equals, and you have to specify that malloc is a C function called memory allocation, malloc. You have to specify that it's going to return an integer pointer. So I'm going to say that, and I'm going to do this. Just say 4. Now, why am I saying 4? Because 4 is the size of an integer, 4 bytes. I could say size of ints. The size of function will do an even better job of doing this. I think I have too many parentheses. There we go. So it'll do almost the exact same thing as the new keyword does in C++. But if you're in C, there is no such thing as new, so you must use malloc. So that's how you allocate a single variable. What if you want to allocate the array, like I mentioned in the introduction to this? Well, you do the same thing. I'm going to say I want to allocate. Let's say I want to allocate. I don't know how much I want to allocate. So let's do a demonstration of that. I'm going to allocate int array ptr. I'm going to make it equal to null ptr. And then what I'm going to do down here is I'm going to come down here and I'm going to say cout, how big of an array would you like? And you could make sure that they put in something, that makes sense. Anything from 0 to 2 million, whatever. You don't want to type in A, B, and C. So how big of an array would you like? So I'm going to say sin array size, which we haven't defined yet, so let's put that up here. And then what I can do is I can say int array ptr equals new int array of size array size. And what this will do is this will take the array size, in this case, let's say the user types a 20, it'll take that 20, automatically multiply it by 4, which is the size of an integer, and it'll allocate 80 bytes of memory. It'll take that address and put it into int array ptr. Now, one thing to remember with new, of course, those of you that are C++ programmers know this. When you're done using an array or a variable using new, you have to say delete int array ptr. You have to delete that array. Same thing here with malloc. If you're going to use malloc, I'm going to say free int ptr. And that will clean up that memory. If you don't do that, you're going to have a memory leak. And if you haven't seen my dynamic memory allocation C++ video, it might be a good idea to take a look at that, because memory leaks are some of the biggest problems in programming today in lower level languages. So now how would I do this with malloc? I would say int array ptr equals, and it's going to return an integer pointer, malloc, and I would say size of an integer times array size. That's the size that the user typed in. So that, and why am I using this malloc? Because that's really what new uses, and malloc is part of the C-only language. And don't forget, you have to free up the array pointer. Oh, and one thing that I missed in this delete, when you're deleting an array, it's always good to say delete square open and close square brackets. Let's make sure I don't get any errors. There we go. So that's what dynamic memory allocation is. You can do this with integers, doubles, chars, even objects in C++, classes, I should say, structures. You can do this with just about anything. But you have to make sure that you clean up the memory after you're done with it. And it looks like we did. We cleaned everything up. So now let's take a look at how you would do this in Linux, and then how you would do it in Windows. Let's start off with Linux. Okay, we're on Linux. I'm on Mint Linux. It's any Linux you want. It works the same way. And what I'm going to do is I need to talk a little bit about the Linux memory model, how Linux actually works. So I'm going to draw a little bit here. And what I'm going to draw is I'm going to draw a simple, just a little block diagram. And let's talk about the different sections of a Linux program. Well, you've got the .text section, right? Remember the .text section. That is the section that contains your code. So that's your program code section. Now remember, when you write program code, the code section is never going to get larger. It's never going to get smaller either, for that matter. So the text section is stored in memory, normally up on top of your application. So it's always going to be stored there. It's never going to get larger. It's never going to get smaller. Then you've got the data section. And that's where you've got your data. That's where you've got your statically allocated variables, like, any kind of a data variable that is not dynamically allocated. You're going to have it in the data. So a lot of times that is actually stored right underneath the text section. And the data section is not going to get larger or smaller either. Now you might argue with me and say, wait a minute, I can dynamically allocate memory. Well, that's not done in the data section, the data segment, I should call it. That's done in the stack segment. So, and then right below the data segment is the stack segment, the BSS. Now, this is where Linux allows you to make things larger or smaller. So your process, your application, gets a certain size of a BSS section. And then when you dynamically allocate memory in Linux, what do you actually do? Well, when you dynamically allocate stuff in Linux, and my eraser is not very big, so what happens is that it takes the BSS section and it makes it bigger. So I'm going to put a dotted line here. This is the original size of my BSS section, and when I allocate additional memory, the BSS section gets bigger. And the pointer right here that was pointing to my that's the pointer to your dynamically allocated memory. So you need to put that into a variable just like we did in C and C++. And then as you add things to the BSX section, let's say we add an array or we add a bunch of stuff, you have to keep track of the address at where you created that. So the BSS section gets bigger or smaller. Now some people might say, well, now what about erasing it, or what about getting rid of that? Well, you're responsible for doing that. You have to go in there and you have to rebuild. I shouldn't say rebuild, that's too strong of a word, but you should reallocate the BSS section to be the size that was given to you when your application started, and that was that first pointer that we created. I always like to create a BSS base variable and put that pointer in there, which we're going to do. And you'll see how you can clean everything up literally with one statement. You don't have to have deletes everywhere. You can just do it with one single statement. So that's how the Linux memory model works, is that you simply make the BSS section larger or smaller. And if you make the BSS section too big and you don't have enough room to make it bigger, the Linux memory manager will handle that for you. And it'll loop around, or it'll go around the memory that's in the way per se. But that's a whole nother discussion about how that works. We're just going to be talking about the code here. So that's the way that the Linux memory model works. Now let's go ahead and let's do some coding. So what I've got here, I've got a simple little program here, and it's I think this is a 32-bit. We're going to stick with 32-bit right now. And let's say I want to allocate a single integer, dynamically allocate a single integer. Now this is kind of ridiculous. You normally won't allocate a single dynamically allocated integer because it doesn't take up much memory. Just make it statically allocated. But we're doing it because we did it in the C and C++ program in the introduction. So what I'm going to do is I'm going to say I'm going to create a variable called intptr. I'm going to define double. Now, in a 32-bit application, you have to say define double. In a 64-bit application, you have to say define quad, because a double in a 32-bit application can store the entire address of anything in memory. In 64-bit, you need a quad to do that. And if you don't do that, you're going to have some problems. It may not even, it's just going to die. You're going to get segmentation faults, big problem. So in a 32-bit application, we're going to say define double, and I'm just going to say make it a value of 0. Now what I could have done is I could have put it down here, which probably reserve double would make more sense. So I'm going to put it down there in the BSS section because it's uninitialized variable. So that's my pointer. Now I mentioned something earlier about I like to keep track. I like to keep track of what the base pointer was, what the bottom of my BSS section was, so I can recover that memory before my program ends. So I'm going to say BSS base reserve double 1. So this is going to contain the original limit of my BSS section. And this is right here. This is going to contain the address of my dynamic integer. Now this is what you would call a pointer. Both of these are called pointers because they contain addresses to memory locations. Okay, so with that said, let's actually do it. So what I'm going to do is the first thing I'm going to do is I'm going to obtain and save limit of my current BSS section. So that's what I'm going to do. So to do that, what I do is I move into EBX 0. Now EBX is the register that tells the operating system where I want to start allocating memory. And if you put 0, that's telling the operating system, I don't want to allocate memory. I just want you to tell me what the limit of my BSS section is. So I'm going to say get the limit of the current BSS section. That's what EBX 0 means. Now in EAX, I'm going to put 45. And this means execute the sysbrk function within the OS. Now sysbrk, I seem to remember I got a definition for brk at one point, but I've forgotten what it is. But that's what it stands for. And then I'm going to say integer ADH. And that, as you know, is pickle to the kernel. Now, how would you do this in 64? In 64-bit, what you would do is you would say RDI is equal to 0, and then in RAX is equal to 0CH, which C is, what is that? A is 10, 11, 12, that's 12. So that's what you would do in 64-bit. And then instead of interrupt 80H, you would say syscall. So that's the 64-bit. And I don't want to have this video be 3 hours long, so I'm just putting those, intermingling those as comments. So that will get me back that interrupt 80 with 0 in EBX and 45 in EAX. That will get me back the actual base, the limit of my BSS section. And what I'm going to do is I created a BSS base. So what I'm going to do is I'm going to move into BSS base EAX. Save the original BSS section limit, section limit. So that's what that's going to do. Now, that is also the statement to say what is the address of the next free area of memory that I can allocate. What is the address of the integer that I'm going to allocate? That's also what this statement does here. What is the base of my current BSS? Remember, in that diagram I drew, the base is where your integer is going to be. So I can also move that into by int ptr, because that's going to be the address of our dynamically allocated integer. Okay, so now we're all set. We've got our pointer, but we haven't actually allocated the memory yet. So what we need to do now is we need to do another sysbrk call, but this time we're going to move into EBX to be at, let's say, the int ptr address. We're then going to add to EBX the size of an integer, which is 4. And then we're going to move into EAX 45 again, and we're going to interrupt 80H. Now, how is this different from the obtaining the base of my BSS section? Well, notice EBX is no longer 0. EBX actually has the address where we want to actually allocate the memory, which was the base of our, or the limit of our BSS section. We add 4 to that, saying we want the base now to be 4 bytes below that, which is going to hold our integer. And then we call the sysbrk and we call interrupt 80H. And that will actually allocate. That will extend the BSS section. Now, one thing to remember when you do this, you want to check to make sure that the allocation occurred. So what I'm going to do is I'm going to compare EAX with 0, and I'm going to jump if equal to memory allocation error. So as long as EAX is not equal to 0 after the sysbreak interrupt 80, we're okay. That means that it allocated it correctly. If it is 0, that means there was an allocation problem. So what I'm going to do is I'm going to create a little label there. We're going to put a no op there for now. And I'm going to jump around it. Okay, a little bit of spaghetti code there, but we'll get through it. All right, so here we go. So this, and I'm not going to put comments in every line of this, but allocate the 4 bytes at the bottom of the BSS section. And I'm just going to put a bunch of semicolons there because the statements above pretty much say what we're going to do. Okay. And this one here is going to be check to be sure it worked. So there you go. Now, how do we actually put data into that variable? Well, what I have to do is I have to move into ESI the address stored in int ptr. So the integer pointer that's stored in memory in my pointer has to go into ESI, and then I move into dereferenced ESI, let's say 99H. So we're going to put data in there. So that's how you do it. It's called indirect addressing. And if you haven't seen my indirect addressing, my array indirect and index addressing video, go ahead and take a look at that. All right, so we've done it. So we've gone ahead and we've allocated and we've put some data in it. We can now use it. We can do whatever we want with it. We're using this int ptr as the address pointer to that new dynamically allocated variable. Now, what if we want to delete it? Now we want to delete that. Well, the way we're going to delete it is I'm going to move into EBX. What was the name of our variable? BSS base. So what I'm going to do is my extended BSS section, I'm now going to say go back to where you were. So I put in that BSS base, I move into EAX 45, and I interrupt 80. Delete our integer variable. So that's the same as a delete. Okay, there you go. Now you might want to also do this. You might want to also say move into int ptr 0h. That will null out the pointer. That way you'll know if it's null that it doesn't have a valid address in it and you won't try to put something into it. So that's really how you then delete it. Now we can go ahead and debug this. Let's make sure that we built it or we didn't have any errors. Oops, we do have some errors. So we have to specify, because this is a dereferenced ESI, we have to specify how big the data is. I happen to know it's a DWORD, and I'm going to do the same thing there. Let's go ahead and build it again. There we go. Now let's debug it. So where is that? There it is. So let's go ahead and do kdbg. And let's put a breakpoint right here, right where we're going to actually move some data into it. So let's see if the allocation works and the data actually goes into it. All right. So EAX, you can see right here, EAX, this is the address of our pointer. That is the address of the integer that we allocated that we ended up, after we did the sysbreak, the second sysbreak. So that's 804D004. So I'm going to go into memory, 804D004, and it looks like it's DWORD. Okay, so right now it's all zeros. So now we're going to move the address into ESI. Let's take a look at the registers. Yep, ESI has that pointer address. We're going to go back to memory, and now we're going to move 99H into the dereferenced ESI. That's this first one right here. And oops, what did I look at? Well, let's double check it. So ESI is 804D004. Let's make sure we did that right. 804D004. That's kind of weird. 804D004. Oh, no, it's not. 804D004 is the new base. Oh, I'm really glad it happened. So when I do a sysbreak, what it does is it extends the BSS section and it makes it bigger, and the address that it returns is the address of the next memory location where you can dynamically allocate memory. Okay, and I wasn't really looking at my registers correctly. When I moved the integer pointer in ESI, it was 804D000. Remember, an integer is 4. So let's change that D004 to 000, and there's the 99 right there. So yeah, that trips me up every once in a while. It's like, wait a minute, you know, EAX contains the new base, not the beginning of the base where my variable is going to be stored. Okay, that's excellent. I love that error. Okay, so now what we're going to do is we're going to delete that memory. And if we go back to registers, our new base for our BSS section is now 804D000 again, which was the original. And we're going to move 0 into the end pointer, and let's just go ahead and continue that. Okay, so that's a single variable. What about an array? How are we going to allocate an array? Well, it's exactly the same way. And what I'm going to do here is I'm going to, just because I like to do things, I'm just going to copy all of this. And now we're going to do an array. So let's put another comment up here. Now, you don't really need this obtain the limit of my current BSS section because we had enough sense to delete it. But you might want to do that if you want to make absolutely sure that you're pointing to the right place. I'm going to leave it in there. You don't really need to have it there. But when we actually do this, instead of doing it to int ptr, we need another pointer up here. And I'm going to call this array ptr. The address of our array. Now I could have used int ptr, but I always like to have a separate pointer for each one of my data objects. So I'm going to say array ptr. Okay, so you could act like we didn't do the first one, and we're just going to do this. We're going to get the base of the BSS section. Okay, so now here it says allocate 4 bytes. Now we copied this from the previous code that we did. Well, let's go ahead and put int ptr into EBX. Now, what if we had the user type in like we did in the C++ program? We had them type in the size of the array that they wanted to enter. What if that's the case? We don't know exactly what the number is in our code. Well, I'm going to do is I'm going to move into EAX. Let's say it was some variable called array size. Okay, and let's do that. Let's come up here and let's create a variable called array size. Define double, and let's say we're going to do 20. So we're going to create an array size of 20. So what I'm going to do is I'm going to move into EAX 20, or no, array size. I'm then going to move into EBX 4. That's the size of each integer, and then I'm going to multiply EAX with EBX. And EAX now is going to contain the total number of bytes. So 20 integers times 4 is 80. It's going to take 80 bytes. So what we're going to do is, we have a little bit of a problem here. We overwrote EBX. So I'm going to move this pointer down here, and I'm going to add EAX. So what I just did was I calculated the size of my array in bytes by doing this, by putting what the user typed in is in a variable, array size, into EAX. I put 4 into EBX. I multiplied EAX by 4, gave us 80. Then I went ahead and put the, it shouldn't be integer pointer. It should be array pointer. So I put the array pointer address into EBX, and then I add EAX, which is the 80 that we did this multiplication of above. We added that to EBX, and then we went ahead and did the normal allocation of the memory. Now let's go ahead and do something with that. I'm going to create a loop. I'm going to call this the fill loop, and I'm going to move into ECX array size. That's the size of the array. I'm going to move into ESI the address of array PTR, and now I'm going to loop. We're going to fill it all up with 99s. So I'm going to move, let's see how we want to do this. I'm going to move into dereferenced ESI because it's going to have the address of each item in the array, a DWORD 99H. And I'm going to add the ESI 4. Why? Because every integer is 4 bytes. And that is going to clean it up. That is going to go ahead and, not clean it up, but fill it all up with 99. And then we've got the delete down here. And instead of int PTR, we're going to change that to array PTR. All right, let's save and build that, see what errors we might have made in the build. Array PTR not defined. I think it's because it's array capital PTR, and it is. So let's all change that to capital PTR. Camel case, very useful as long as you remember that that's how you wrote it. All right, let's try it again. There we go. Now let's debug it. So I still have my single integer allocation in there, and I can keep it in there no problem. But what I'm going to do is I'm going to come all the way down here. That's where I'm going to start my dynamically allocated array code. I'm going to run it. And let's just go ahead and run it one line at a time. This looks like the address of our array, what it's going to be. Okay, I put array size into EAX. Oh, I forgot to dereference it. So I have the address of array size. Oops, error. So let's go ahead and dereference it. And I believe I did that again. Yep, I did that here. So, but I did it right. All right, let's try it again. The breakpoint should still be there. It is. Okay, so now we're going to put array size into EAX, which is a 20. You can see down there in the registers panel. I'm going to move 4 into EBX. I'm going to multiply EBX into EAX. Now we've got 80. That's the size of our array in bytes. Now we're going to go ahead and allocate that memory. We're going to check to see if EAX is 0, which it's not. It's A04D050. Remember, that is the address of the next free area. That's now the address of the base of it. Our array PTR is going to contain the address of where our array begins. Okay, it didn't have a memory error, so I'm going to put array size into ECX, the address of array pointer in ESI, and the address of the array pointer is 804D000, and there it is right there. So now I'm going to look at the array as I fill it up with 99s. And you can see the 99s changing down here. Okay, I'm going to go ahead and put a breakpoint here, which is where I'm going to delete it. I'm going to put the base into EBX 45, interrupt 80. It now cleaned up the memory. You saw a big change in the debugger down here below because we really don't have access to that anymore. And then we're going to clear out the pointer. Now, one thing to remember when you're doing memory allocation in Linux is that as you make the BSS section larger with the sysbrk call, as you create the dynamically allocated objects, you need to delete them in the opposite direction, or don't do anything with them until at the very end. You can just go ahead and do this at the very end. So I could actually put this right here under end it all. And what this will do by doing it down here is it'll delete everything because you're putting the original base. When your process started, you're putting that original base address and you're doing a sysbreak there, so it's going to automatically delete everything in a single statement. So if you do that, you don't even need this anymore. Up here when we did our single integer, you don't even need that delete there anymore because you've got it all right here. You're deleting everything in one pop. And you may also want to do the same thing for the pointers. So you can move in an NPTR the DWORD 0H. And that will null out the pointer. So you're also nulling that out. Now, do you really have to do that? Do you have to null them out since your program is ending? You can see it's about to end down here. I like to do it because if you don't null out the data, there's still data in memory at that location, and a hacker might be able to get into there, especially if you had something like a password or account balance or something like that. So it's always a good idea to null those out. All right, so that's how you do this in Linux. Try it out yourself. We're next going to start on Windows. Okay, we now have a Visual Studio Windows program up and running, or to edit. I always say up and running. It's not running. Visual Studio is running. And I did increase the font a little bit here. And if you want to know how to do that on Visual Studio, you go up to Tools, Options, and you go under Environment, Fonts and Colors, and you specify the larger font or the smaller font that you want. Let's take it up to 16. So it makes it a little bit easier to edit and a little easier to see. Okay, so in Windows, the allocating of memory in Windows is done basically the same in the program, but instead of actually doing interrupts to the operating systems, you're calling Windows built-in functions in assembly language that are going to do that calling for you. And there's a number of functions you might be needing, and I'm just going to paste them all in here, and we can talk about each one. So the GetProcessHeap, what the heap is that it's a heap of memory. It's just a big bucket of memory that Windows allocates to your application, your process, when you start the process, and the heap is a certain size. And what you can do is you can use memory within that heap. Now, how do you use the memory? There's a thing in Windows called a Heap Manager, and you ask the Heap Manager to go ahead and give me some data. Give me some data when I do a new or a malloc. HeapAlloc, so GetProcessHeap, you need that. You need to know what the heap is because it's used down here in heap allocation. So there's your heap. So you've got to have your heap to be able to send it to the heap allocation. And then you can also create another heap. You can destroy a heap. You can free up a heap. Now, you're not actually freeing up the heap. You're freeing up the memory that you've allocated within the heap for you to use. And you can also get the size of the heap. So there's all kinds of things you can do here. We're mainly going to use the get heap process, and we're going to use the free, and we're going to use the allocate within the heap. So let's go ahead and get started with that. So just like in the Linux version, if you haven't watched the Linux version, I really recommend that you do. So what I'm going to do is we need to get the heap first. So I'm going to say heap pointer, and I'm just going to define double, and I'm going to uninitialize it. Now I'm defining it as a double because this is a 32-bit application, and addresses in 32-bit applications are 32 bits, which are 4 bytes, which is 8 times 4 is 32. If it was a 64-bit application, you'd say define quad. So that's my heap pointer. Now that is going to be the actual address of my heap. Now I also need a pointer for each one of my dynamically allocated memory objects. So we're going to do two. I'm going to create a simple integer, and they all have to be doubles, and I'm going to have an array. So we need those 3 pointers. We need this one to get the address of our heap where all of our extra memory is located. We then have pointers for each one of the dynamically allocated variables. And the reason, again, that I put a question mark there is that we have no idea what the value is, so why initialize it? Okay. So let's do like what we did in Linux. Let's allocate a simple integer. Now, before you allocate anything, you need to get the heap pointer. Now, before we actually, I'm going to put it above that because this heap pointer can be used for every allocation. This is one of the things that I like better about Windows than Linux, is that heap pointer is the base of our, I'm not sure if they use the BSS section in Windows. It's a completely different memory model than in Linux, but we're going to go ahead and do that. So what I'm going to do is I'm just going to invoke GetProcessHeap. And what that does is that goes and finds out what is the address of my heap. And I'm going to move that address into the heap pointer from EAX, because that function doesn't take any arguments. It simply puts the address of the heap into EAX, and now we're saving it. So great. So that's what we're going to do. Okay, now we want to actually allocate some data. We actually want to allocate some data within the heap that we can use. So to do that, I'm going to simply allocate a single integer. I'm going to invoke the heap allocation function, and we have to include the heap pointer. We include 08h, which means fill up the bytes that we allocate with zeros, and I want to allocate 4 bytes because that's a single integer. So we're going to allocate the variable, our 4-byte integer variable, and then what's going to go into EAX is the pointer for that variable. So I'm then going to move into intptr EAX. So let's put some comments here. allocate the 4 bytes and fill with zeros. Save our memory address. And now I can go ahead and put some data in there. Now you do it just like you do in Linux. I'm going to move into ESI the address stored in heap pointer, and then I'm going to move into dereferenced ESI. And in Windows it's a little bit different. A DWORD starting at the pointer, and we're going to put 100H in there. So save 100H in our variable. All right, great. Now, just like in Linux, we have to delete it. We have to delete that when we're done with it. And I'm just going to delete it right underneath it. And to delete it, we use the HeapFree function. So I'm going to say invoke HeapFree. And we have to give it the heap that we're actually deleting from. I'm not really sure what that 0 is, but you just always use a 0. And then it happens to be the variable. So we're going to delete the int ptr memory from the heap. And that does the delete. All right, so let's go ahead and build this. And I think I've got, oh, yep. It's HEAP, right? Yep, HEAP. Let's build it again. All right, looking good. So just like on Linux, we can debug this. I'm going to go ahead and put a breakpoint right here before we actually put data into the dynamically allocated memory, and let's go ahead and debug it. All right. So let's take a look at, so here's int ptr. Let's go into memory, and I'm going to say ampersand int ptr. And right now we're looking at bytes. Let's right click on this and looks at 4-byte integers. There's the address of our variable, of our integer, dynamically allocated integer. So what we're going to do is, that's the address of the integer. That's not the address of the data. That's the address of the, this is the pointer that points to the data. So to actually look at the data, it's D7-1F68. I have to say 0x D7-1F68. Okay, right now it's all zeros. Remember when we allocated it, we used this 08H, which told it to fill it up with zeros. So we're going to move that pointer to this memory area. We're going to move that into ESI. And now we're going to move 100H into the dereferenced ESI, which will be this location. And you can see 100 has been put in there. So that's how we actually dynamically allocate an integer and then use it. We're going to go ahead and free it up. Notice the data has changed within it. The free does something to the data. And then we're going to go ahead and continue the program. So just like we did in Linux, that's how you do it in Windows. But you're calling functions instead of actually doing interrupts. Now, I believe, and I haven't actually seen the Windows code for that, but I believe you probably are doing that. You probably are doing interrupts, but these functions, built-in functions for Windows, helps you out. Okay, so now let's go ahead and allocate an array. So let's allocate an array. Now, in the Linux version, we had another variable here. We had array size, and we called it 20. Now, array size can be something the user's typed in. Like you might question the user, like we did in the C and C++ demo, how big would you like this array? They type in 20, it goes into this variable. So let's mimic that instead of writing all that code. Let's go ahead and mimic that that's something the user typed in, array size of 20. So let's dynamically allocate the array. Now, we already have the process heap. We've got it in the heap pointer, so we don't have to do it again here. But what I want to do is I want to take that 20. So I want to do 20. I want to do 20 integers, and each integer is a size 4, right? So I'm going to move into EAX, array size. I'm going to move into EBX, 4 because an integer is 4 bytes, and I'm going to multiply EAX with EBX. So what we're doing here is we're calculating the size in bytes of our array. We need that information because we have to tell the HeapAlloc function how many bytes we want to allocate. So that's now an EAX. Okay? So let's go ahead and put that into some variable because we kind of need it because the HeapAlloc requires there to either be a literal constant in there or it has to be a variable. So I'm going to say array size bytes, define double question mark. So let's go ahead and put that into array size bytes. So now we know exactly how many bytes that we want to allocate for our array. So let's go ahead and now say invoke HeapAlloc. Heap pointer is the same. We want to fill it up with zeros, and we're going to say array size bytes. So that's going to allocate the array. Now, one thing I didn't mention that I mentioned in the Linux is that after you do this, you've got to check EAX. So I'm going to compare EAX with 0. If not equal, jump if not equal to allocation error. And that can be any label you want, right? So I'm just going to put that down here. And we'll put a no op there. Really what you should do is you should print something to the screen that, hey, you had a memory allocation error. There's a problem. And I'm going to call this end at all. And if everything is okay, we're going to jump end at all. Okay. So if it allocated okay, then EAX will have a number in it. If it doesn't have a number, if it's 0, actually it should be jump if equal. Oops, not if not equal, jump if equal. So if EAX after the HeapAlloc is 0, we need to go to allocation error. Allocation error right now will do nothing. You might want to put an output in there. But if it doesn't equal to 0, then it's going to jump to end it all, which is down here. But we're not done yet, so we're not going to jump to end it all just yet. Okay. So now that we've allocated it, let's go ahead and let's do something with it. So I'm going to create a loop. I don't know, let's call it fill loop, just like we did in Linux. And let's do something with it. So I'm going to move into ECX array size. That was the number of items in the array that we allocated. I'm going to move into ESI the address. Now, we didn't actually save the address here, so we have to save the address of our variable into a pointer variable. And here's our int array pointer, so we're going to use that. So let's move into int array ptr ex. Now, if you're a little bit lost, that's my fault because I didn't really do everything in the correct order. So after you do a heap allocation, you've got to save the address, just like we did with the single integer up here. You've got to save the address that the heap allocation allocated for you into a pointer variable. So that's what we did. So because we're going to need that, right? Okay. So now let's move that because we're going to use indirect addressing on this loop. So we move the address of the memory that we stored in int array pointer. We move that into ESI. Yes, we could have moved EAX, but what if we did something in between there, right? What if we did something in between this line and this line that affected EAX? And you never know when that's going to happen, so I went ahead and did it this way. Okay, so let's go ahead and move. Let me see, what do I want to do? Let's move all 99s in there. So I'm going to say move in a dereference ESI, a dword pointer 99h. Let's add to ESI 4 because each integer is 4, and that should be it. So that should fill up the array. So let's put some comments in there. The size. No, let's not say the size, the number of integers in the array. The address of our array. And I think this is pretty self-explanatory, but I love comments. Put 99h into the array location. And in Windows, of course, you have to say DWORD pointer. And then here, go to the next item in the array. All right. Now we're still not done yet because we need to delete it. So we need to free. So once we're done with it, we're going to say invoke HeapFree PTR. And we called it int array PTR. Now, of course, you're not going to fill it up with numbers and then just delete it. You're going to do something more with it. But I'm doing it here just as a demonstration. All right, let's save and build this. Be amazed if there's no errors. I'm amazed. Now let's go ahead and see this debugging. Now what we're going to do is we're going to bypass the thing that we did with the integer, and we're going to come down here to our loop, put a breakpoint there. Actually, no, let's not do that. Let's put the breakpoint on the compare after we try to allocate the array. And let's debug it. Okay, so we did the heap allocation. I'm going to take a look at registers. It looks like EAX does have an address for our new array, so it should not jump. It did not. I'm going to move that address into the int array pointer. I'm now going to move into ECX the number of items in the array. Hexadecimal 14 is 20. I'm going to move the address of the int array pointer into ESI. There's ESI. It has that exact same value in it because we didn't do anything with EAX, so they should have the same value. Now we're going to go ahead and let's take a look. The address at ESI, let's go into here, and we're going to have to do a little memory here. 106.8.048. 106.8.048. 106.8.048. Okay. Notice all these zeros. That's because we said to zero fill it. And now we're going to go ahead and just fill it up with 99s. So you can see the memory is just filling up with 99s as we go through the loop. I'm going to put a breakpoint on the heap free. You can see all of the variables are all the data in that array are all 99s. Then we're going to heap free it. Also notice it did not zero out the array. It's the same on Linux. So if you've got some data in that array that you don't want to be touched by some hacker or some other program, it might not be a bad idea to put a loop in there and zero it all out when you're done with it. That's how security problems occur, is that you leave data in memory, you don't think about it. And we're going to jump to end all, and that's going to end the program. So not too bad. All of these prototypes I'll go ahead and put into the description of the video so you can see those prototypes. You can look these up on the internet because there's a lot you can do. Let's say you fill up your heap, you need to get another heap. Well, you can ask the heap manager to create you another heap of memory. So you can have multiple heaps. You have to keep track of both of them, right? Because you need them both. But you can have multiple heaps of memory if you run out. Okay, so that's our dynamic memory allocation both on Linux and Windows. Watch it again. Try it out. You're not going to be good if you don't try it out. Hope to see you in our next video.